So in this section, we want to analyze the derivatives of functions and try to graph those derivatives. So we're going to take a look, for starters, at this curve, which looks like it might be a cubic curve, and we're going to try to graph its derivative. So first, I want you to look at points x equals a and x equals c, and let's think about what the tangent lines would look like there. So right here is the point where x equals a, and if you were to draw in your tangent line there, the tangent line would be horizontal. And remember, horizontal lines have a slope of 0. So what that means is for this x value, here that x value was x equals a, we're going to be plotting a y value of 0 because that is the slope at that point. So at x equals a, we're plotting a y value of 0 because that represents the slope at that point. Now we're going to do the same thing at the point x equals c. So on the cubic curve, at the point where x equals c, if you were to draw your tangent line, and remember the analogy that if you were driving your car along this road and you stopped here at this point, you can imagine where your headlights would shine, and that path where your headlights shine, that's your tangent line. So our tangent line would be horizontal here as well, which is another slope of 0. So for this x value of x equals c, we're also going to plot a y value of 0. So our y values on this graph represent the slopes of the curve at those x values. And this is certainly something that I always want you to start with. Always start by looking at the curve and trying to determine where the tangent lines would be horizontal, because those are easy slopes to identify. They're slopes of 0. So now answering this question, the tangent lines at x equals a and x equals c are horizontal. So the slope is 0, where x equals a and x equals c, which means that the derivative is equal to 0 there. So now let's take a look at this first interval from x equals 0 to x equals a. So that would be this portion of the graph. So for this portion of the graph, we want to imagine our tangent lines. So you could even try to draw in a few tangent lines if you wanted to. And notice that these tangent lines all have a positive slope. So from x equals 0 to x equals a, the graph is increasing. Those y values are getting larger. The graph is increasing, which causes the slope to be positive. So from x equals 0 to x equals a, we have a positive slope, which means that our derivative is going to be greater than 0. So I'm going to go ahead and just gently shade then where the derivative is going to live. In other words, between 0 and a, we're going to be plotting positive y values. So if you can imagine, the derivative is going to be living here above the x-axis, because in this shaded region, our y values would be positive. So now we'll look from x equals a to x equals c. So that would be here we go. That would be this part of the graph. So between a and c, the graph is decreasing, which means if we looked at the tangent lines would have negative slopes. So the slope is negative. And remember, the slope is the derivative, so if the slope is negative, that means that our derivative is negative. So between a and c, we will be plotting negative y values. So if you can imagine, the graph is going to live somewhere below the x-axis between a and c. So let's go to the bottom of the page and try to recap what we've talked about so far. Again, remembering that we're trying to plot the derivative. So at the points x equals a and x equals c, the slope was 0. So we're plotting y values of 0. And then between 0 and a, the slope was positive. So we said we expected the derivative to live above the x-axis. we're going to be plotting positive y values. Between A and C, we said that the slope would be negative. So between A and C, we'll be plotting negative y values. So the graph is going to live below the x-axis. So now let's look at the next bullet point and take a look at where the tangent line has a slope that is most negative. So going back to our original graph, in this orange region here, we said this was where the slope was going to be negative. So where in this region is the slope the most negative? And I would say the slope is probably the most negative somewhere maybe about there. And that might be close to the x value of b. So that means that when x is equal to b, we're going to be plotting a y value that will be the most negative. So back to my graph here, at x equals b, I'm going to plot a y value here that would be the most negative. So I'm not exactly sure how negative it is because I haven't actually included a scale here, but it's just important that I plot a y value. At x equals b, that y value needs to be negative. So let's go fill in our bullet here. So where does the tangent line have a slope that is most negative? That would be at x equals b. So therefore what's going to happen is we're going to have the most negative y value plotted, which is going to tell us that our derivative is going to have a minimum at x equals b. So now let's finish up by going to the x values that are greater than c. So once again, back to our original graph, if we take a look at the right-hand part of the cubic, here my function is increasing again, so my slopes are positive. So for x is greater than c, the graph is increasing, which means that the slope is going to be positive. And since the slope is our derivative, then that means our derivative is greater than 0. So on our graph, we're going to end up with a derivative that lives above the x-axis. We're going to plot positive y values. So the most important takeaway right now is just to continue to remember that the y values of our derivative function represent the slopes of the original function. So now we have 3 points plotted for our derivative. We see that we have two x-intercepts, and then we have this minimum point at x equals b. So let's try to figure out the basic shape of the rest of the graph. So I'll go back to the original function, and let's take a look at the tangent lines at the beginning of the function. So if you were to draw in your tangent line somewhere near the beginning, it might look like this. And that's a pretty steep line, so the slope there is not only positive, but it would be a fairly large number. Whereas if I analyze a point a little bit closer to the maximum, again imagining that you're driving your car, maybe you're right here. Now my tangent line, it still has a positive slope, but it's not as steep of a line, so the slope is smaller than it was before. So my slopes, although they are positive, the slopes are actually decreasing. So coming back to my derivative graph, that means that my y values are going to start out really positive, and then my y values are going to decrease and come to this x-intercept. And then, back to our original graph, if we take a look at my tangent lines, again, I had a horizontal tangent line there, which was a slope of 0. So now if I keep moving, I start to have, if I could draw a good tangent line for you, a little bit better, I start to have tangent lines that have a negative slope. And we agreed that it would be the most negative here at x equals b. So my slopes are going to turn negative and become really negative at x equals b. And then my slopes are going to be going back towards 0 at x equals c. So back to your derivative graph, your y values are going to get really negative. They're going to hit that minimum, and then they're going to be going back to 0. And then finally, the right-hand side of the cubic, my slope is 0 at x equals c. And then if I start to draw in some of those tangent lines, I notice that the tangent lines, the slopes are getting larger, more and more positive. So my y values on the derivative are going to go positive and then grow, and become more and more positive. So this parabola-shaped graph would be the graph of my derivative. And in fact, we'll study later why the original graph was cubic, and that caused our derivative graph to be 1 degree less, which would make it quadratic. So a function that is degree 3 will automatically have a derivative that is degree 2. We'll study that a little bit later. But again, remembering the y values of the derivative graph are the slopes of the original graph. That's really important, which is down here at the bottom. Remember, the derivative of a function at a point is the slope of the tangent line at that point.